So, that is it. It is the end of the course that we are coming into. This is worldwide, I guess, would be the end of the first introduction to multivariable calculus. After that, various aspects go into various things. Means somebody can be interested in the Lagrange multiplier rule and optimization, somebody can be interested in differential geometry, but everywhere you will see the role of calculus and multivariable calculus, and that is essential to understand. And that is the message of this course, that calculus is stupendously useful for our modern civilization. Today we are going to speak first about Gauss divergence theorem, and then I will speak about miscellany. Some interesting facts we will put in and blah 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 things, and we will talk about several issues pertaining to something to fields, something about curl, something about divergence. So, we are going to talk about Gauss divergence theorem, which relates surface integral with volume integral. Volume integrals are triple integrals. So, they are done over dV, are related to surface integral is related to volume integral. Anybody who has done some mathematics and says that he has never heard the name of Carl Friedrich Gauss would be a sin against mathematics. Carl Friedrich Gauss was probably one of the greatest mathematicians of our times, and he I hope you won't mind if I take a cup of tea. So, this would be a much more relaxed session. So, he taught in a place called Göttingen, and I had been lucky to visit, at least stand in front of the observatory of Carl Friedrich Gauss. I visited his grave, and the city of Göttingen, which is a university city and which has a very famous university. If you walk through the streets, you will see all the famous names appearing out, written in various houses. Okay, Hilbert stayed here, Gauss stayed here, and so and so. So, Gauss had an immense contribution to mathematics, whether it is algebra, whether it is geometry, whether it is about numbers, and of course, Gauss had an inkling of the idea of non-Euclidean geometry, a revolution which was led later on by Riemann, Lobachevsky and many other mathematicians. So, unfortunately, though many of us in mathematics try to do research, try to do something, we think that we are trying to make a progress, making a little progress about our subject, about our ideas, trying to answer the questions we have. But I do not know, maybe fortunately or unfortunately, I have no idea what to say, but I want to say that mathematics only celebrates its best, and Carl Friedrich Gauss is definitely one of the greatest ever. Carl Friedrich Gauss is one of the immense contribution of this divergence theorem is because they all come from a geometrical angle. This contribution of divergence theorem has immense applications to fluid mechanics, to electricity, to several other things. So, let me just write down. So, our aim would not be to prove the Gauss theorem, because we have shown one proof of Stokes theorem. What we would be doing is state the Gauss theorem, give one example of the Gauss theorem, maybe two if you want, 2, 3, 4 more in fact, and that would be our aim. And once that is done, we will go into miscellaneous topics. So, what does the Gauss divergence theorem says? It is sometimes called the divergence theorem. So, what does it say is that, so consider a volume W, consider a body W, and the boundary del W is equal to S is a surface. So, it could be a body like this. It is much more better to teach math on the board than on this strange screen. Certain things, for certain things old is gold is really true, for certain things not. So, here is a body, it is a kind of a 3-dimensional body. A 3-dimensional body, and this 3-dimensional body W, and there is a surface. This surface is del W, del W, which is S. And you have a field, continuously differentiable vector field defined on W. See, whenever we are talking about field, I have already mentioned, a field is a vector valued function whose all components are continuously differentiable. That is, when I am talking about a field, I am actually talking about continuously, all the components to be continuously differentiable. That is what I have mentioned when I have spoken about fields. So, fields are vector valued maps, but we will call those vector valued maps fields which have all their component functions continuously differentiable. So, this is a criterion that we have. So, let F be a field, F be a field defined on a domain, defined on a domain containing W. So, maybe you defined on W, whichever you want to say. F be a field defined on a region containing W, field defined on a region containing W. Then the Gauss divergence theorem says, why the name divergence comes is this. So, if you take the divergence of the vector map, you take the divergence of this and you integrate. So, this becomes a scalar function, because divergence of V is a scalar function. I will tell you what is it, and that is equal to the S. Now, what is this? We have spoken about dot products, but we have not spoken about divergence. So, delta dot F is called the divergence of the field. So, why do I write it like this? So, let F, the field F has 3 components. By now you are habituated to the fact that these are all functions from R3 to R, f of xyz, f1 of xyz, f2 of xyz and f3 of xyz. So, I write f2 and f3, that is what I have written. And now what I will do when I am talking about dvef, I will write down the del operator, which you already know from yesterday. And that dot product with, I am not writing in the form ijk, does not matter, the del operator and dot product with f1, f2, f3, and you know, you think as if I can do a dot product operation. Of course, these are not numbers, but assume that you can do it. So, you multiply this with this. So, del x of f1. So, this means that this by definition del dot f is del x of F1 plus del del y of F2 plus del del z of F3. This is actually the definition of divergence of F. So, this is equal to the surface integral of F. So, the volume integral, the divergence volume integral of the divergence of S is equal to surface integral of S. So, it could be that sometimes the surface integral is difficult to compute, but it is much more easier to compute this one. So, let me first start by showing you some simple examples related to the divergence theorem. I want to also say that f dot ds, so ds can be at any point s. So, if you take a normal at this point, it is pointing outward like this, but this normal can be viewed to have three different angles, alpha, beta, gamma. So, with the x axis it has alpha angle, with y axis it has beta angle, with z axis it has gamma angle, alpha, beta and gamma. So, it is alpha, beta and gamma. So, when you write here f dot, when you write f dot ds vector, you already know that this is nothing but f dot n hat ds, but n hat now can be actually written as a component wise. So, if f is of the time f1 I vector plus f2 j vector plus f3 k vector. So, the coordinates of the tip of n, so here is a surface, here is my n, and here I have, I think by my imagination I can bring the x axis, y axis and z axis. Now, so there is angle alpha with this, angle beta with the y axis, angle gamma with the z axis. Now, if you keep on dropping through the tips, you will get back x axis, y axis, z axis. So, you will get the distance of y if I drop from here a perpendicular on the y axis. If I drop a perpendicular on the x axis, I will get the x coordinate. Or so, if I view it like this, as if the 0 is, I have drawn the normal at 0, then what happens is, then I can write this normal in the following way: dot product with the normal can be written as, so what would happen if I drop a perpendicular here on the x axis. So, what is the length it will cut off? It will cut off a length which is n, which is same as the norm n of cos alpha. So, norm n is 1 because it is a unit vector. So, other cases it will have norm n of cos beta, norm n of cos gamma, and norm n is 1. So, the three components, so the three coordinates are cos alpha, cos beta, cos gamma. So, I can now write it in terms of the three coordinates. Basically, this is nothing but the coordinate representation: cos alpha, cos beta, you need not write in terms of the coordinate also. This cos alpha, cos beta, cos gamma, these are called direction cosines. This actually tells you which direction the normal vector is pointing to at the given point, and that will give you f1 cos alpha plus f2 cos beta plus f3 cos gamma into ds. So, that is also another way of writing this vector. So, you can write it as, so if you write the integral, so integral of, so double integral over del w, which is s, which is equal to s f dot ds is the same story over, you can have this alternative form of writing also. Now, let us look at some examples. We will not give the proof of the Gauss divergence theorem here. If there somebody wants a proof, if you can make a request of that on the thing, we will put up the proof in the portal. I think you have already received your proof of the Taylor's theorem for second order derivatives in the portal. Okay, so I take an example from the book. So, example 1. And example 1 says, okay, f vector is given as 2 xi vector plus y square j vector plus z square k vector, and S be the unit sphere and S be the unit spheres. So, its volume is the unit sphere and everything inside it, that is the V, the W. So, del W is this unit sphere, that is it. So, I ask you to evaluate the line integral. So, that is what the book asks you. Of course, you can evaluate the line integral yourself. So, suppose I want to evaluate the line integral myself. So, I have to first find the n vector. So, I represent it by spherical coordinates x, y, z, and then I write the n vector. You know what the n vector is, phi cross u, or write ds vector is the phi u cross phi v vector into du dv. So, I have to do that parameterization and do all those tremendous calculations. So, that would be a mess, of course. You would not like to go into that sin theta cos phi, that kind of messes. Some people can enjoy it, the trigonometric, playing with trigonometry, but many people might not. In these scenarios where you have to write, things can go out of your hand, the calculation, the Gauss divergence theorem, somebody knows, will try it using the Gauss divergence theorem. They will say, okay, let me compute the volume integral of the divergence of f dv. So, what is my f? The divergence of f is very simple. I will take del f del x. Here the divergence of f is very simple. It is 2 plus 2y plus 2z, and this is dx, dy and dz. So, What does it tell me? I can take the 2 outside. One plus y plus z dx dy and dz. Now, what are the range, because it is a unit circle, what are the range in which they are varying? X is varying from 1 to -1, y is varying from 1 to -1 to 1. So, z is also varying in this zone. Maybe there are much simpler ways of doing it. Now, we will see what happens. So, you have 2 times integral v dx dy dz, which is dv actually, plus integral v y of dx dy dz, plus integral v z of dx dy dz. So, let us now, I know what is this integral. So, it is 2 times integral v dv. So, 2 times the volume of v it will become. So, there is a 2 everywhere, sorry. 2 times now integral v y dx dy dz. See, once I can evaluate this integral y dx dy dz, I can evaluate the other one also. You can write w here instead of v if you want, does not matter. Now, let me try to evaluate this. So, let me just evaluate first with respect to x, or maybe with y, does not matter, it is the same. So, y dx dy dz. Let me see whether I have put the things correctly here. So, I made a mistake by putting -1 at every point, sorry, that is we are in a hemisphere, it is a sphere. So, we have to first look how z is varying. Z is varying over these minus root over 1 minus x square minus y square to root over 1 minus x square minus y square. Then how is y is varying in terms of x, and then x is varying from -1 to +1. So, we have done an, this is the kind of thing we can easily do. Now, then if we integrate in first dz, then that is what you will have, because y is constant. Now, let us look at this part of the integral. Two y root over 1 minus x square minus y square dy. Now, let us set a is equal to 1 minus x square, sorry, root over 1 minus x square. So, a square is equal to 1 minus x square. Okay. So, I can write this whole thing now as, this can be written as minus, because x is fixed in this case, minus 8, because we are just integrating over y, 2y root over a square minus y square dy. Now, I will make another substitution, set y square is equal to t. If I set y square is equal to t, it means 2y dy is equal to dt. Now, when y square equal to t, so t will have how many limits? When y square equal to minus a, it has the limit a, t is y square, and when y square is equal to a, it has the limit a. So, this integral becomes a to a square minus y square is t and 2y dy is dt. So, it is a to a 2y dy is 0. So, ultimately this integral would be 0. So, this is the important thing, that integral w y dv is 0, and by symmetry we know z dv is also 0. So, once you know, then this integral, so these two parts are 0. So, this is nothing but 2 times integral v dv. This is nothing but 2 times integral v dv, and what is dv here? It is a sphere, it is a 2 times 4/3 pi r cube, r is 1. So, 4 by 3 pi r. So, the answer is 8 pi by 3. So, that is the answer of the surface in tan. Now, this is, and by Gauss theorem I know that this is equal to, that this is nothing but the volume integral of, and that is exactly the answer. So, here we have the answer. Okay. So, we have done one example. Let me show you another important result, which is called Gauss's theorem, and that is used for gravitational potential and electrostatic potential. So, it is called the Gauss's results. This the result is due to Gauss, a result due to Gauss. Sometimes called the Gauss theorem. So, this is given in the book, the famous book of vector analysis by Spiegel. I think this is a book which you can always take for practice. Vector analysis by Spiegel from Schwamm series, published by McGraw-Hill. This is an exceptionally good problem solving book. So, there are a lot of problems and you can try and practice these problems. Please take a look of this book. I will just write the name on the top, vector analysis. Okay. Now, let me look at this problem. The problem says that suppose there is a spherical body. So, here I have the coordinates, and there is a spherical body outside the coordinates. So, there is a spherical body. So, essentially so this is the origin, and the origin is outside the body. So, this is your volume V and this is the surface, S is del V, the spherical surface, the sphere. Now, the question is that show that this integral of S, it is n dot r, r is a radius vector of any point on the surface. Of course, since O is outside, none of them is x, y, z, but none of them has value 0. X, y, z, none of them are 0, 0, 0. So, R is not a 0 vector, n vector, R vector, R cube, this looks like gamma. So, let me just write it again. R vector ds. So, they are asking you to show that this is 0. So, here F is the field R vector by R cube. So, the value of F, the numerical value of F is 1 by R square. So, suppose there is a force field whose magnitude is just inversely proportional to the square, and let inversely proportional to the square of the distance, right. Then, so field whose magnitude is just 1 by R square, then I have to show that this is 0. So, basically the whole thing is written as F dot n ds over S, and this is nothing but by the Gauss divergence theorem now divergence of, since R is non-zero, this divergence turns out to be 0. It is not very difficult to compute this, I leave it to you as a exercise to compute. And hence by Gauss divergence theorem what I get? So, this implies integral S f dot n ds, and what is f dot n? If I write down the f dot n, it is simply f is r by r cube. So, it is nothing but r dot n, which is same as n dot r with the commutativity of the inner product. Yes, a dot b is same as b dot a ds, and this is 0, because this is equal to this, and now this is 0 because of this fact. So, this is also 0, and hence I have this. Now, there is another question where also the Gauss divergence theorem will play a role, but it is a very subtle one, and we will learn a lot of things while doing it. It says that no, now let the hemisphere spherical region be such, let the spherical region be such that 0 is inside that spherical region. So, the origin lies at the center of the spherical region. So, here is a volume, I draw a volume V, so at the center lies the origin O, now I want to now I am Gauss asks the questions, what is the next question Gauss asks is what is this? Now what is this? Now evaluate, now find the same question, the same surface integral. What is this? Is it 0? The answer unfortunately is not, it is not 0. Because when you are talking about finding the divergence, you are finding the divergence. If you look at this theorem beforehand, look at this application here in page, I have skipped 221, okay. So, look at this application here. When I am computing this grad dot f, I am computing it at every point of the volume. I can do this here at every point of the volume, because at no point of the volume r becomes 0. But here I have a problem. Here I have a problem, because 0 is the center of the sphere is itself the origin. So, 0 0 0 is there. So, when I compute grad d dot f is not defined at that point. So, grad dot f here, my f is the same, f is, but it is not defined. So, what is the technique? By what technique I can overcome it? And here is a technique which is typical to physicists, and that what we are going to do. We draw a small ball around O, a small sphere whose center is the origin, and basically we target out and we now look at the volume V dash. So, we call this the big volume V, and this small volume we call it V naught, and we at V dash. So, V dash is every element in V, but nothing in V naught. So, kind of thing like that. So, it is a region bounded by that V. So, not, I should not write it like this, but V dash is the region bounded by S, and I will call the boundary of this sphere as S naught. S naught is del V naught, and this is del S is del V is S. This idea is linked to gravitational potential. We are doing physics, actually mathematical physics. So, what I am having is bounded by the region S and S naught. Now, I want to integrate. So, now if I want to talk about the integral over both S union S naught of f dot ds, then this is actually, because these are all two disjoint surfaces. So, over S f dot ds, just like you have for line integral, if you have disjoint curve, one curve which then another curve, then another curve. So, the whole thing is path is broken into some pieces of curves, then you do it over each of the curve, or if you have the holes, so you do the line integral over each of the holes separately and add them. Okay. But by this definition, but we also know by Gauss divergence theorem V dash, which is a region bounded by this volume. So, del dot f, and in this region there is no x y z with all the coordinates 0, r is not 0 here, dot dv is same as integral S union S naught f dot ds. So, what we know is that because in V dash the vector r is not equal to 0, del dot f, that is del of r vector by r cube is equal to 0 in V dash. So, what do I get? I get, now this is written as a sum of two integrals. So, basically I get integral s f dot ds, f is obviously r vector by r cube, is equal to minus integral s naught f dot ds. So, I have to find this. So, if I evaluate this, so basically now I want to evaluate s naught n r n vector dot r vector by r cube ds, and that is what I am going to now evaluate. If I can evaluate that, I have actually made a move forward. Okay. Now, let me look at it in a slightly different way. So, now what I am trying to do, this is a problem described in Spigel, but I am doing it stepwise and describing you in very simple way. Now, let the radius, let us look at page, now let the radius of this small sphere S naught, this be A, this be A, and observe. So, here I had 0, I had taken a small sphere out and then there was a big sphere. So, I am looking at the region in between. So, basically if you take a cross section, so it will look like this. So, 0 is sitting here and you have taken this out. So, you are essentially bothered about this zone. Now, this is my radius A here, value of the radius, but any normal on this surface corresponding to the given volume is in the direction negative to the radius, because the direction of the radius is always away from the origin this way, and here it is towards the origin. You have to understand this part, this hole here is not a part of the volume is here. So, this is a surface, this is a surface. So, if you have a cylindrical thing like you must have seen coils which travel by train, you know, the aluminum sheets coiled up like this, and there is a hole. So, or you can take some papers, you can take a lot of paper together, some 7-8 papers, and make a hole like this. So, there is a thick inside, there is a biggest boundary and a smallest boundary. So, there are two surfaces, one is the outside surface, one is the inside surface, but if you go inside the inside surface and look at the inside surface, the normal will point towards you. So, normal will point inside, and that is the key thing, the normal will point inside. That is the key thing to remember, and once you note that, then you know, let me write the r vector is nothing but minus a of n vector. So, n vector is unit vector, so norm r is a, n vector is a unit vector along the radius. So, in this case because of the symmetry of that spherical symmetry, you have all the n vectors along the radius. So, this is what is there. So, my f vector n dot r by r cube. So, r cube, so the radius r in this particular case I am looking at the field values on this boundary, because I want to find it on S naught. So, this is my S naught and this is my boundary S. So, I am trying to find the field values on the boundary. So, finding f, computing values on S naught. So, I can write this as n dot minus a n dot, and r cube, r is a, so it is a cube, r is a on the radius, on that S naught sphere r is a. So, it is minus a n dot n by a cube, but this is 1, n dot a is a unit vector. So, it is minus a by a cube, that is minus 1 by a square. So, integral of S naught n dot r by r cube ds is equal to integral r minus 1 by a square S naught ds. So, what is the area of that surface? Area of the surface is 4 pi a square because it is spherical thing, minus 1 by a square ds of S naught. So, that is minus 1 by a square 4 pi a square. So, now integral of S n vector dot r vector by r cube ds. So, I am writing this part here is equal to minus of this integral, which is minus of 1 by a square 4 pi a square, because that is the volume of the area of the surface 4 pi r square. So, this is nothing but 4 pi. So, this is the answer. So, when 0 is inside, there is a beautiful simple answer which is 4 pi. It is amazing how pi comes out at many places. So, we have a pretty good description here of Gauss divergence theorem, the application of the Gauss divergence theorem. So, we have two good examples showing you the application of the Gauss divergence theorem, which I have computed in total, and we have given you an explanation of the Gauss divergence theorem. There are many things associated with the Gauss divergence theorem, which maybe one of them I will speak in the next class, which is a kind of there is the Gauss divergence theorem can talk about flux, which I have not spoken about a lot of things about physics, but because I do not want to get into physical problems of physics, then I will be teaching a physics class. Flux of a fluid or flux of an electric field, all these things are important, and Gauss divergence theorem plays a very important role in such cases. So, my job as a mathematician is to really tell you the theorem and tell you some of the problems where it can apply, but I am not going to discuss too much of physics or continuity equations and all these kind of things. So, that is left to the physicists to discuss. So, because there can be a lot of questions that will come up, which we might need the help of physicists. So, we are not going to get into that kind of domain at all. We are stick to our mathematical domain. In our next class, where we are going to talk about how we are going to sum up everything that we have spoken about, we are going to on our way maybe prove something at the end or do something just to talk about fields and this whole idea that we have come out. Fields have played a very important role. The notion of a field have been very key to our understanding here, and that is what we are going to talk about a bit, how we can get a little further idea about fields and how we can mathematically handle them. Maybe we will speak a bit about it in the next class, and which is a sum up class. So, that ends this ends the course actually, this ends the course. So, you have done quite an amount of stuff. It is a huge amount of material told to you in 8 weeks time, which I think it is a maybe 23-24 hours lectures. So, I think this is not so, there is a short time and a lot of material been pumped into this course. So, but what I want to say is that it needs a lot of practice, and many cases you might get stuck, you might get suddenly okay, you write the wrong limits, which can happen with me. I also wrote the wrong limit today. So, because you can just get carried away, but suddenly you understand and you put the things. So, think over the problems, never hurry with a math problem. If you So, stuck with a math problem for 2 days does not tell you that you are mathematically incapable. Maybe you are actually very capable, maybe you are making a deeper thinking, maybe you will find a much better way to do it than others. So, with this I would rather end my talk, and I thank you for all of you for actually very patiently going through this course. Hope that you have enjoyed it as I have enjoyed delivering this course to you. It refreshes sometimes as we researchers keep on focusing on our own research problems, looking at research papers, current research papers, trying to ask questions, trying to answer them. Research is a very different ball game. I do not know whether I am myself a researcher. Maybe I am more interested in understanding when I read new research, I have some questions and I try to answer them. Sometimes I fail, sometimes I partially answer, sometimes possibly I can get some nicer ideas. So, who knows, maybe the whole of my life I would just keep on doing incremental work in mathematics, but whatever little work that I do in research gives me a lot of joy. But as we keep focused on our research, sometimes we get lose touch with basic mathematics, and if we are stuck in something we have to rush and look at our books. This is very common. Please get out of the feeling that okay, if you have learned a particular, suppose if somebody has taken some expertise in electrical engineering and expertise in communications, he should remember each and every problem that he has learned in his first calculus 1 course or a multivariable calculus course. Please do not think of that. If you need it, go back to the books. But once you have done a course, these names like Gauss divergence theorem or Stokes theorem or Green's theorem will never leave your memory. These names should remain imprinted in your memory. The curl, divergence, gradient, dot product, cross product, these all should remain ingrained in your memory, and that is what the message that I want to give. If these names are there, if you need them, just open a book and see them. So, thank you very much. We will come back for a brief sum up of what we have done, maybe a 15 minutes lecture trying to tell you some things that we have done here, some things that we have learnt here. So, thank you, that is essentially the end of the course, and there will be 15 minutes of some summarizing what we have done and hoping that you have enjoyed it.